In graph 12.3, we showed how we can take horizontal slices of production frontiers with two inputs and then depict those production frontiers in two dimensions as maps of isoquants, much as we depicted consumer preferences as maps of indifference curves. We can now take the lessons we learned from indifference curves and transfer those to what we can see in isoquants. One of the main features of isoquants is that they contain information about how substitutable capital and labor are in production, just as the shapes of indifference curves indicated how substitutable goods were for consumers. It may, for instance, be that the production technology is such that the isoquants that emerge from slicing the production frontier horizontally take on a shape that's relatively flat. Or it may be that these isoquants contain some curvature, as they did in the derivation in graph 12.3. We can then ask, just as we did in the consumer case, what the slope of an isoquant means. Take, for instance, the input bundle A, where we use 2 hours of labor and combine it with 10 units of capital to produce 100 units of output. If the slope at point A is -3, then that means we can go down by 3 and over by 1 and end up roughly on the same isoquant as we started. In other words, we can substitute 3 units of capital with 1 unit of labor without altering the level of output that we produce. This is called the technical rate of substitution, or more accurately, the marginal technical rate of substitution, but we'll usually use the shorthand TRS for technical rate of substitution to indicate such a slope. This is very analogous to the concept of a marginal rate of substitution for consumers, where the marginal rate of substitution indicated how much of the good on the vertical axis is needed to substitute for one of the goods on the horizontal axis and keep the consumer just as happy as she was originally. Just as consumer indifference maps could range from those that were close to perfect substitutes to those that were close to perfect complements, so isoquant maps can range between those same extremes. In panel A, we have isoquants that are relatively flat, indicating that the substitutability of capital and labor in production doesn't vary very much along any particular isoquant. In other words, the technical rate of substitution doesn't change much as we move along an isoquant. In panel C, on the other hand, that technical rate of substitution changes a lot as we move along an isoquant, and it's somewhere in between in panel B. We would therefore say that the isoquant map in panel A represents a technology for which capital and labor are relatively substitutable throughout, whereas the isoquant map in panel C represents a technology for which capital and labor are relatively complementary and therefore have to be used together. You can already look ahead and see what kinds of implications this will have for optimal choices for firms. If the firm has a production technology that treats capital and labor as relatively substitutable, then as the prices of capital and labor change, the firm will be easily able to substitute from one input to the other and still produce the same amount. But if capital and labor are relatively complementary, then as wages and rental rates change, the firm won't change much about how it ends up producing any given level of output.